Hey everyone, welcome back to the channel. Today we are going deep on one of the most practical topics in health tech engineering: how to actually build production grade pipelines that move patient data safely between hospital systems, the cloud, and your database. We are covering HL7, AWS, and PostgreSQL, all connected into one real world story with real code you can reuse. Let's get into it. Here is the roadmap. We will start with HL7 basics so everyone's on the same page. Then move into AWS architecture, both the high level picture and the low level, step by step data flow. Then we write real Node.js code to parse HL7, walk through 3 use cases you will actually see in production. Model everything in PostgreSQL and finish with the stuff most tutorials skip: error handling, dead letter queues, and HIPAA grade auditing. Quick context on why this matters. Even though everyone talks about FHIR and modern APIs, the reality is most hospitals today are still pushing HL7 version 2 messages around admissions, scheduling, lab results, all of it. So if you want to work in health tech, you need to understand this world. My goal for this video is simple. By the end, you will be able to read a raw HL7 message, design a serverless pipelines to process it, model the data in Postgres, and just as important, handle it when things go wrong. So why does this actually matter? Hospitals run dozens of different systems that don't naturally talk to each other. When that breaks down, it's not just inconvenient. A clinician might be looking at outdated patient info, billing gets delayed, and the regulators are pushing hospitals hard toward a better data exchange. But here is a thing that I want you to notice: every one of these problems is really a data pipeline problem underneath. Reliable receiving, correct information, correct transformation, consistent storage, safe retries. That's actually what we are building. Let's talk about why this is actually hard. HL7 version 2 messages are plain text, separated by pipes and carets, Node.js, not XML, and traditionally, hospitals wire these up point to point. One system talks directly to another through an interface engine. The problem is, if that connection drops, you can lose a message, and there is often no real retry queue behind it. What we actually want is durable buffering, decoupled processing, automatic retries, and a proper audit trail. That's the shift we are making today, from fragile wiring to a real distributed pipeline. Let's demystify HL7 version 2. It's a messaging standard from the late 80s, and instead of JSON or XML, it uses plain text with pipes to separate fields and carets to separate subcomponents inside a field. It's event driven. A patient gets admitted, that's an event, and it triggers a message. And even though FHIR gets all the hype today, HL7 V2 is still what's actually running in most hospital interfaces right now, usually sent over a protocol called MLLP on top of plain TCP. Every HL7 message starts with a message. The message header field 9 is the important one. That's the message type, like ADT caret A01 for an admit. Right after that usually comes PID, the patient identification segment, which is where you will find the medical record number, the patient's name, date of birth, and address. Look at the row text at the bottom. See how everything is separated by those pipe characters. Once you can count fields like this, HL7 stops looking scary. Three more segments you will see constantly. PV1 covers the patient's visit, what unit they are in, who the attending doctor is. SCH is all about scheduling, appointment type, and status, which we will use for our scheduling sync use case. And OBX is used for lab results. Every single result value, like a glucose reading or a blood pressure number, comes in as its own OBX segment. A single lab message can have dozens of these stacked one after another. Here is a complete real HL7 message and admit event. Let's read it together. A message tells us it's ADT caret A01 and new admission. EVN confirms what when it happened. PID gives you the patient John A. Doe, medical record number 10029. Born March 15th, 1980, and PV1 tells us he's in ICU room 101 under Dr. Jane Smith. That's it. That's the whole message once you know where to look. These are the three messages. These are the three message types we will work with all video. ADT for admissions and demographics, SIO for scheduling, and ORU for lab results. I picked these three on purpose. They are not academic examples, they are the exact message types powering real integration projects in hospitals right now. If you understand these three deeply, you understand probably 80% of what a healthcare integration engineer deals with day to day. Here is the 30,000-foot view of what we are building. The hospital's EHR sends an HL7 message over MLLP. We land the raw message in S3 first. Always keep the original untouched. From there it drops into an SQSQ, which is our shock absorber. It decouples receiving from processing. A Lambda function parses and validates it. Step functions orchestrates whatever business logic that message type needs. And finally it lands in PostgreSQL. And running underneath all of it, CloudWatch and SNS are watching every stage, so we know the second something breaks. Why go serverless instead of running a traditional interface engine server? A few reasons. S3 gives us cheap, durable, immutable storage, perfect for an audit trail. SQS absorbs bursts, like when every unit does its shift change updates it at once. Lambda scales automatically up and down to 0. Step functions gives us retries and error handling almost for free, with a visual trace of every run, and CloudWatch ships built in. Put it all together and you are not paying for idle servers waiting around for the next HL7 message. Now let's zoom into the actual mechanics step by step. An MLLP receiver accepts the TCP connection and immediately sends back an acknowledgement that's part of the HL7 protocol itself. Before we do anything else, we archive the raw message to S3, organized by facility and date. That S3 write triggers an event that drops a message onto SQS. A Lambda function picks it up, parses the segments, and validates the structure. The step functions then routes it based on message type. We write to Postgres inside a transaction. And at every single step, we are emitting structured logs and metrics to CloudWatch. Let's actually look at what this looks like in the AWS console. Here is our S3 bucket. You can see the raw HL7 files landing, organized by facility and date, and that highlighted row at the bottom is the lab result message that just came in. Right below it, the SQSQ dashboard, three messages available, one currently in flight being processed, and the oldest message is the only 4 seconds old. Zero messages sitting in the dead letter queue, which is exactly what you want to see on a healthy day. Here is the processing layer live. 3 Lambda functions, one per message type, all green, all running in under 100 milliseconds. And below it, look at this. This is an actual step functions execution graph, and I have caught it mid-run. Parse, validate, and transform are already done. Shown in green, persist is running right now. That's the blue one. Notify hasn't fired yet. This is exactly the kind of trace you had pull up in a real incident call to see precisely where a message is stuck. Let's tie it all together and trace one real message from start to finish. It lands in S3, gets queued in SQS, step functions runs it through parse, validate, transform, and persist, and it ends up as a row in PostgreSQL. And here is the CloudWatch trace for that exact message. You can see every single stage time stamped down to the millisecond, landed at S3 at 11:45 and 11.203 millisecond, and by 11.45 minute 11.1744 millisecond. It's a fully persisted 541 milliseconds start to finish. That's the entire pipeline we have been building actually working. Let's write a real code. The lambda function gets triggered by our SQS queue. First, we split the row message on line breaks to get each segment, MSH, PID, PV1, and so on. Then, for each segment, we split on the pipe character to get the individual fields and store everything in a simple object keyed by a segment name. Now HL7.msh1 8th position of array uh, gives us the message type. HL7.pid the 5th position gives us the patient name. Yes, libraries like same simple HL7 exist and can save you time, but I wanted to show you the raw mechanics first because it makes debugging real production issues so much easier. Once we have split the message into segments and fields, the next job is turning that into clean structured JSON, something a normal application developer can work with or with without ever thinking about pipes and carrots again. The function pulls the piece out of PID and builds a proper patient object. From here, we hand that JSON off to the next stage of the pipeline. This is really the boundary line. Everything everything before this function is HL7 world. Everything after is just normal application data. Use case number one, real time scheduling sync. The moment someone books an appointment in the hospital scheduling system, it fires an SIU S1 message. Our pipeline picks that up and syncs it into Postgres within seconds, not overnight, not on a batch job. That same table when then feeds the patient portal, the reminder text service, and provider dashboards. And it's not just new bookings, reschedules, cancellations and modifications all flow through the exact same pipeline, just with different trigger code. Here's the SIU message next to the SQL that handles it. Notice the appointment ID that becomes our conflict key in Postgres. We use insert with on conflict to update. So whether this is the very first time we see this appointment or the fifth time because someone modified it, the exact same query works correctly. That's what idempotent means in practice, and it's the difference between a pipeline that's safe to retry and one that quietly creates duplicate appointments. Use case 2, patient demographics. ADT A01 and A04 create the patient record. A08 updates it, think address changes or corrected spelling, and A03 discharges the encounter. The real engineering challenge here isn't parsing the message, it's building one accurate golden record per patient that when data might be coming from multiple source systems. So my approach I will be like, don't overthink the branching logic. Treat every demographic carrying ADT message the same way offset by MRN. It's simpler and it naturally handles messages arriving out of order. Same pattern as before applied to patients. We extract the fields from PID into a clean object, then insert into the patient's table keyed on MRN. Notice how similar this SQL looks to the appointment upsert from the last use case. That's not an accident. Once you have built one item potent upsert pipeline, you have basically built the pattern for all of them. Use case 3 lab results. An ORU R01 message can carry many OBX segments, one per result. Look at this example: a glucose reading of 182 flagged H4 high against a normal range of 70 to 110. That H flag matters. It's exactly the kind of thing that should trigger an alert to a clinician, not just sit quietly in a database. We also always keep the raw message alongside the structured value, because in healthcare, being able to prove exactly what was received is just as important as the data itself. So notice this table is append only. Unlike patients or appointments, we don't observe lab results. If a result gets corrected, that's a new row with status C, not an overwrite of the original. That's intentional. For clinical data, you generally want a complete history of every value that was ever reported, not just the last one. On the code side, parse observations simply filters for OBX segments and maps each one into a clean object ready to insert. Here is the data model that ties everything together. Patients sit at the center. The MRN is the key that appointments, lab results, and the audit log all reference back to. Providers is its own small lookup table, and audit log is deliberately separate from the clinical tables. It tracks every message we have ever received by control ID, idempotent, independently. It's not what to say like by control ID, independent of whether that message succeeded or failed. That separation matters a lot once we get to the HIPAA auditing slide. Here is the actual DDL you had run to stand this up. Patients is the root table, MRN is as the primary key, appointments and lab results both carry a foreign key back to the patient. Nothing exotic here on purpose. The right data types, sensible constraints, and clean foreign keys will take you a lot further than clever schema tricks. I'll link the full schema, including indexes, in the description below. So resilience starts with one simple rule: never let a clinical message just disappear. But not every failure deserves the same response. If a database connection times out, that's transient. Retry it with exponential backoff and it will probably succeed. But if the message is missing a required segment or reference a patient we have never heard of, retrying isn't going to fix that. That's a permanent error, and it should go straight to a dead letter queue for a human to review, not get retried 5 times and quietly vanish. Let's trace exactly what happens when a message fails. It's sitting in the main queue. Lambda tries to process it and throws an exception. SQS will redeliver it a few more times. That's the retry limit, the max receive count. If it keeps failing past that limit, the redrive policy automatically moves it to the dead letter queue. That's not the end though. A CloudWatch alarm fires the moment anything lands in that DLQ SNS page that the on-call engineer. And once the root cause is fixed, that same message gets redriven back into the main queue and reprocessed. Nothing gets lost and nothing gets silently retried forever either. This is the slide HIPAA auditors actually care about. Two rules: log structured JSON so it's queryable, and never put raw PHI in a log line. Hash the patient identifier like you see right here, and here's what that looks like live in CloudWatch logs insights. I have run a query filtering for this exact SIU message, and you can trace it landing in S3 getting parsed, persisted, and even see warning where the notify step got throttled and retried. That level of traceability is exactly what holds up in a compliance review. So before this ever touches a real hospital, run through the checklist. On the security side, encrypt everything at rest and in transient. Give each lambda the bare minimum IAM permissions. Keep RDS in a private subnet and make sure there is a signed BAA with AWS. That's the legal backbone for handling PHI in the cloud. Operationally, always design around an item potency key. Keep your row archive forever and watch SQS queue depth. It's usually the first sign of trouble long before lambda errors start piling up. So let's recap. We built one complete serverless pipeline that takes row HL7 off the wire, archives it, parses it, orchestrates it, and lands it safely in Postgres. That pipeline powers three real use cases: scheduling, demographics, and lab results. All of the same idempotent pattern, and it doesn't fall over when things go wrong. The with retries, data queues, and an audit trail that would hold up in a HIPAA review. If you want to build this yourself, the full source code and SQL, you can directly take reference from the PPT. It's quite simple, not just a very complex code that I displayed to you. If this kind of practical health attack content is useful, hit subscribe and let me know in the comments which use case you want to see me build live next. So thanks for watching. I'll see you in the next one.